Welcome to this section on PV cells and modules. In this video, we'll explore how solar panels work, the different technologies behind them, and how to get the best performance out of your solar power system. Let's begin our journey into the world of solar energy. Every solar system, whether it's on your roof or part of a solar farm, has a few key parts: solar modules or panels, inverters, and mounting structures. If it's an off-grid setup, it also includes battery energy storage system to store electricity for later use. To understand the construction of a PV solar system, one, invariably, thinks of PV module first, which is the lifeline of the whole system. Let's understand the components of a PV module in a hierarchical order, from the smallest component wafer to the largest system array. A solar chip is a general term often used interchangeably with a solar cell or wafer, depending on the context. Let's understand hierarchy of components of a PV module. A wafer is the ultra-thin slice of semiconductor material, usually crystalline silicon, that serves as the base material for manufacturing solar cells. It is the raw, unprocessed foundational component. Large-scale solar farm. A solar cell, or photovoltaic PV cell, is a treated and processed wafer that has the electrical properties needed to convert sunlight directly into electricity, direct current, or DC, through the photovoltaic effect. The term solar chip is less common, but can refer to this individual, functional unit. A solar module is a single, self-contained, pre-assembled unit made by connecting multiple solar cells together in a series or parallel circuit. These cells are encapsulated between protective materials such as tempered glass and a backsheet, and framed in aluminum to create a durable, weather-resistant panel. Solar panel is the consumer-friendly term for a solar module. A solar array is the complete power-generating unit made up of multiple solar modules or panels that have been electrically wired and mounted together. It is designed to produce a specific amount of power to meet an energy need and can range from a small rooftop system to a large-scale solar farm. A solar cell converts sunlight into electricity through something called the photovoltaic effect. When sunlight hits the cell, it excites electrons inside a semiconductor, creating electric current. Photons from sunlight strike the semiconductor material, usually silicon, in the solar cells, knocking electrons loose and creating electron-hole pairs. The inherent electric field within the semiconductor, created by its N-type and P-type layers, forces the freed electrons to flow in one direction and holes in the other, generating a direct current, DC. This flow of electrons through an external circuit produces electricity that can power devices by converting to alternating current, AC, for household use. There are different types of solar cells, each with its own benefits. The most common ones are monocrystalline and polycrystalline silicon cells made from silicon crystalline wafers, similar to the wafers used to make computer processors. We also have newer types like thin film, perovskite, and bifacial cells that can capture sunlight from both sides, resulting into enhanced absorption of solar energy. The most efficient type is monocrystalline mono, manufactured using the well-known Czochralski process. Made from a single silicon crystal, these are highly efficient and have a uniform, dark color. They are more expensive than polycrystalline, but offer superior performance, especially in high heat. Made from single, pure silicon crystals, these panels have a uniform, dark color. They are the most efficient type, performing well even in low light conditions. Monocrystalline. Half-cut solar panels are most popular panels because of their techno-commercial benefits. Made from melting multiple silicon crystals together, these panels are less efficient than monocrystalline but are cheaper to produce. They have a speckled iridescent blue appearance. They are less expensive than monocrystalline panels, but also less efficient. These are made by depositing one or more thin layers of photovoltaic material onto a substrate, such as glass, plastic, or metal. They are less efficient than crystalline silicon, but are flexible, can be cheaper to manufacture, and perform better in high temperatures and diffused light. Made from various materials, including amorphous silicon, these panels have a lower efficiency and a shorter lifespan compared to crystalline silicon panels. They are often used in specific applications, like RVs, boats, or industrial rooftops. This is a manufacturing technology applied to crystalline cells to increase efficiency by adding a layer on the back of the cell to reflect light that would have been wasted. These panels can capture sunlight on both their front and back sides, increasing their energy output. They are well suited for ground or flat roof installations where light can reflect off the surface below. These modules use lenses or mirrors to concentrate sunlight onto small, highly efficient solar cells. They require direct sunlight and are best suited for areas with high solar irradiance. An emerging technology with high potential for efficiency and flexible, low-cost manufacturing. These use multiple layers of different semiconductor materials to capture a broader spectrum of sunlight, leading to very high efficiencies, but they are currently more expensive and used in specialized applications. Available solar panel wattages range from small residential panels between 350 W and 400 W to large commercial panels up to 650 W or even more. Monocrystalline panels have the highest efficiency rates, often exceeding 20%. This means they convert more sunlight into electricity per square meter, which is ideal for limited roof space. Because of their high efficiency, you need fewer monocrystalline panels to produce the same amount of power as a larger number of less efficient panels. Monocrystalline panels can last 30 to 40 years, which is longer than polycrystalline 25 to 30 years, and thin film panels 10 to 20 years. The uniform black color of monocrystalline panels is often considered more aesthetically pleasing and modern compared to the speckled blue of polycrystalline panels. Monocrystalline panels are more effective at generating power during low light conditions compared to polycrystalline panel. Assess your household's electricity consumption to determine the system capacity you need. Higher efficiency panels produce more power from a smaller area, which is crucial for limited roof space. Look at the panel's wattage to understand its power output and consider maximizing the total wattage that can fit in your available space. Choose panels with a lower temperature coefficient, as this indicates better performance in hot climates. Opt for panels with a low annual degradation rate, ideally below 0.8%, to ensure consistent power production over time. Efficiency tells us how much of the sunlight hitting the panel actually turns into electricity. The fill factor measures how effectively a cell uses its available area. Higher efficiency means better performance and more power per square meter. Following factors directly affect the solar module operation intensity: weather, shading. The area of installation must be shadow-free and dust-free as far as possible. Panels lose efficiency as they heat up. For maximum efficiency, solar panels should ideally be south-facing in the northern hemisphere or north-facing in the southern hemisphere, and tilted at an angle approximately equal to the location's latitude, which is the mean angle. For optimum efficiency, the panel angle may be changed from its mean position by -15 deg in summers and +15 deg in winters. In India, panels should face true south, and the optimal tilt angle is governed by the above rule: cleanliness, age, and quality. Other factors include the efficiency of the panel itself, wiring resistance, and inverter performance. Cleanliness of the panels is a very important parameter directly affecting the performance of the PV modules. Therefore, regular cleaning of the panels is very crucial for the best results. Panels are tested under standard test conditions, STC, 1000 W per square meter of sunlight, and 25 degrees Celsius cell temperature. But real-world conditions are often hotter, and sunlight varies, so manufacturers also list nominal operating cell temperature, NOCT, values that better represent daily performance. Advanced module designs like mono-PERC, half-cut cells, and bifacial modules help improve performance. They capture more light, reduce heat losses, and generate more power, even in low light or partial shade. Installing panels correctly is key. They should face the equator, true south in the northern hemisphere, true north in the southern hemisphere, and at the right tilt angle, which is vital for optimizing the absorption of solar energy, as mentioned at point number 5 above. Keep cleaning the panels using soft water and cloth to prevent dust buildup that blocks sunlight. Solar panels come with 2 main warranties: a product warranty usually 10 to 12 years, and a performance warranty around 25 to 30 years. PV panel quality is ensured through adherence to international standards like those from the International Electrotechnical Commission, IEC, and organizations like Underwriters Laboratories, UL, which test performance, durability, and safety. A common problem is faced quite often that PV module breakage test, also known as a module impact test, simulates mechanical stress to evaluate a solar panel's durability and safety, especially concerning glass breakage. The test typically involves dropping a weighted impactor, such as a shrapnel bag filled with lead shot, from a specified height onto the panel's center to check for cracking or shattering. While this is a mechanical test, other tests like electroluminescence (EL) testing are used to find hidden defects like microcracks. To wrap up, solar modules are the heart of every PV system. By understanding how they work and taking care of them properly, you can enjoy clean, renewable energy for decades. Thanks for going through and reading. Don't forget to like, share, and subscribe for more solar insights from I-SED Academy. Please go to I-SED Academy platform for detailed learning about solar technologies.